So a simple model for resolving forces, we could imagine we have some sort of flat surface. So let's just say this is some sort of, road. And we have something on the surface. So it could be a box or a car or something like that. And we've got two people who are pushing it in this direction. Or pulling it in this direction, sorry. So they're pulling it that way, what other forces must act on the particle? Well, there's going to be some sort of weight acting down, and of course, if there's a weight, what stops it going through the plane? Well, the normal reaction going in the opposite direction, perpendicular to the plane. Okay, what else could we have? We could have friction going in the opposite direction to motion. So if they're pulling it to the left, friction will go right. So just putting some labels on here: F for friction, R for the normal reaction, W for weight, and we'll have T for thrust. Okay, so here's a basic model of it. Let's assign some values and see if we can solve it. So let's say the two people who are pushing it are providing a combined force of 100 newtons. And the friction as a result of the movement is, let's say, 70 newtons. Okay, the weight is, let's say 80 newtons. And of course, because it's not coming off the plane or going through the plane, the normal reaction must be equivalent to the weight. So 80 newtons here as well. Okay, so I've already solved part of it there. Let's consider vertically and horizontally. First, vertically. This is really easy. I've basically just said it. So we've got 80 newtons and 80 newtons. One's going in one direction, one's going in the other. So the resultant force vertically is the 80. So I'm taking upwards as positive, by the way. So it's 80, which is our normal reaction. Take away the weight, which is 80. So the resultant force in the vertical direction is just 0 newtons. Okay. The horizontal direction, if we take this way, because that's the way that they're pulling it, as positive, then considering the horizontal direction, we will have 100 newtons. That's positive because that's the way we chose as positive. You can choose either way you want, but because we know it's moving that way, I'm going to just choose that way as positive. So we've got 100 newtons. Take away, well, what's going in the opposite direction? 70 newtons. So what will be the resultant force? 100 take away 70. So 30 newtons. So we could perhaps draw another model of this and draw the resultant forces on. So we would have the box. There's no vertical force. We just have one arrow going this way. That's 30 newtons. Okay, so that's the resultant force. Resultant force. Okay. Okay, so on a tilted plane, it becomes a little bit more challenging to resolve the forces, but let's imagine we have some sort of hill. So there's our hill. That's at 30 degrees. We have a car that's going up the hill. There's the car. And that's providing some sort of thrust from its engine up the hill. So we'll label that T. Then what other forces will we have? Well, the car will have some weight, which of course acts vertically downwards. So we'll label that W for weight. Then what stops the car coming through the plane? Well, there must be some sort of normal reaction. So that's always at 90 degrees to the plane. So there's our normal reaction that we label R. And then there'll be some friction because the car tyres aren't perfectly smooth, neither's the road. So there'll be some friction, which always goes in the opposite direction to motion. So it'll go that way, and we'll label that F for friction. Okay, so there's our basic forces. Now, on a flat plane, we would just think about vertical and horizontal. We can do that here, but it becomes a bit more complicated because of this angle. An easier way of doing it is if we consider parallel to the plane and perpendicular to the plane, because you can see all of our forces except its weight are already either parallel or perpendicular. So we'll take parallel up the plane as positive, and we'll take perpendicular out from the plane like that rather than through the plane as positive as well. Okay, so what will the resultant forces be? Well, let's say that the particle is in equilibrium, or the car is in equilibrium, which means it's not actually moving. The friction at the moment is too high, let's say. Okay, so what would happen with the forces? How can we work them out? Well, parallel to the plane, the only forces we have are the thrust and the friction. The thrust is easy, it's just T, and we could just say T equals to F, but we have a better way of finding F and an easy way of working it out. We'll see that in just a sec. Is there anything else that acts parallel to the plane? Well, this here, the weight, is going to apply some sort of force down the plane, and it's also going to apply perpendicular to the plane. Okay, now we need to work out how much of that force it applies. So I would draw a little triangle, and we can then use trigonometry. So if I draw, yellow is not the best colour, let me pick purple there. So take purple there. That's a right angle triangle, so we can use SOHCAHTOA. Obviously, the weight here is the hypotenuse, and we can work out the other sides. This angle, of course, would be 30. So the opposite, which is parallel to the plane here, would be the force acting parallel to the plane, of course. How would you work out the opposite using SOHCAHTOA? Well, whatever the hypotenuse is, times sine 30 would give you the opposite. So we could then say T equals F plus whatever our weight is, so W, sine 30. Okay, that's the component acting parallel to the plane. Now, let's consider then acting perpendicular to the plane. So there's one that's immediately obvious, and that's R acting perpendicular to the plane. So let's take R equals, and what's going in the opposite direction to that? Well, some component of weight. Okay, well, what component of the weight? Look at our right angle triangle here again. You can see this is the adjacent to the angle. So how would we work out the adjacent? That would be W, because that's our hypotenuse in this case, cos 30. Okay, so you can see now this is parallel to the plane and this is perpendicular to the plane. So here we've got parallel or perpendicular. Now, of course, we could have solved this horizontally and vertically, but that becomes a lot more complicated because in this case, we only had to consider the components of one force. We considered the weight. To make everything else horizontal or vertical, we would have to consider three forces. So we'd have to consider this one, and this one. You can see it can be done, but it becomes a lot more complicated. So we'll just stick with parallel or perpendicular to the plane. So an important thing to remember when resolving forces, especially when working on a tilted plane, so for example a hill, or angles that aren't horizontal or vertical, is the fact that sine x and cos x have to take on certain values. So sine x is between -1 and 1, while cos x is also between -1 and 1. But what relevance does this have? If I imagine this plane here and we've got some sort of particle on it, its weight, whatever it may be, will act completely vertically downwards, okay? And that's fine, but if we want to consider parallel and perpendicular to the plane to resolve our forces, then a component of this will act down the plane and a component of it will act perpendicular through the plane, okay? So, if you're solving for these two forces here, so you've got this one that's perpendicular to the plane and this one here that are both components of W, and somehow you get either of these to be bigger than W, then you've definitely done it wrong. Because if it's W sine our angle, so our angle here, or W cos our angle here, so sine would give us this one, cos would give us this one. If it's somehow bigger than W, then you've definitely done it wrong because these are always between -1 and 1. In theory, it could be equal to it, but it's unlikely because the angle would have to be either flat or perfectly vertical for those to work out, which obviously in this case is not. That's not what we're considering. So a good thing to remember. So sometimes we're given forces in vector notation. So for example, we could have F1 is 2i plus j, some brackets around there. And then we could have F2 is 4i. We could have F3 is 3j. And we're taking I as the horizontal direction, so sort of the x direction. And we're taking, horizontal. And we're taking j as the vertical direction, So going straight up, or sort of the y direction if you're using coordinates. When trying to work out resultant forces in this sort of form, you do it exactly as you would in normal algebra. So if we wanted to do F1 plus F2 plus F3, we would just add together the respective I and j components. So we'd have 2i plus 4i plus no i's in this case, so 2i plus 4i, we'd get 6i. Work out the respective j components. We've got 1j here, no j's here, and 3 more here. So 1 plus 3 would be 4j. Okay, so the resultant force of all these acting on a certain particle, if they're all going in the same direction, that is, then would be 6i, so 6 newtons in the horizontal direction or the x direction, and 4 newtons in the vertical direction or the y direction.